Okay, part B of this question, that is AS2 Physics 2 Jun2005, question 5. Okay, so it's part B. Is an interesting question because this is a development of the Young's double slit and the use of the equation, but it is using, you can see here, a signal generator connected to two loudspeakers. So what we're producing here is we're producing an interference pattern down at the bottom along here. So we get a high sound, low sound, high sound, low sound, high sound, low sound going across here. So we've got a series of equally spaced maxima and minima with a maximum in the center. The distance from here across to here, that's D in the equation. The distance from A to B, that will be the distance A in the equation, and the distance from H to H and H to H, that will be the distance Y. So the question actually occurs on the next page, right? And if we take a look at that question, then it says, at P, the center point of CD, the sound level is high, but when the connections to one of the loudspeakers are reversed, the sound level at this point changes to a low level. Explain fully why the sound level is first high, but then changes to low. Okay, so a high sound is produced when the waves arrive in phase and superpose or interfere constructively. And you could use superpose or interfere there. So superpose or interfere constructively. Changes to a low sound, okay? When the loudspeakers are reversed, then the waves arrive at point P out of phase and interfere destructively. So that means in the first instance, when they arrive at P, they arrive in phase, we get constructive superposition, constructive interference, and the waves enhance each other to produce a high sound. Whenever then we reverse the speakers, what happens is they arrive out of phase and we get destructive interference, and so they cancel each other out. Next part of the question is a calculation. Speed of sound is 330 meters per second in air. The mean distance between a point of high sound and point of low sound is 1.52. Assume that equation 5.1 applies and calculate the frequency supplied by the signal generator. First thing I would probably point out here is this. It's between a point of high sound and a point of low sound is 1.52. So this particular phrase here, that's indicating not the distance y but half that distance. So the first thing that we have to do is say that y is actually equal to 2 times that 1.52 meters, and that's actually equal to 3.04 meters. Now we can use the equation that we had before, which was that lambda is equal to a times y over d, but we need to get some information from the previous diagram to give us what a and d are. So again, if we take a look at the previous diagram, what we see is the distance between A and B is 65 centimeters. Again, I would straight away just say 65 centimeters, just be careful with that. That's 0.65 meters. So we're going to have to change that when we're doing the calculation. And then the other distance that we need is from the slits to the screen, which in this case is 6 meters. So when we go back over the page, we can see that A was equal to 0.65 meters, 65 centimeters, and D was equal to 6 meters. Therefore we get lambda to be equal to 0.65 times y, which is 3.04, divided by 6. And when we put that into the calculator and work that out, that turns out to be 0.33 meters. Now that's only part of the calculation because we've just worked out the wavelength. We're actually looking for the frequency, and again if we go back up into the question, we can see in the question we were given the speed of sound is 330, and so that brings into play the use of the wave equation. V equals F lambda, therefore 330 is equal to F times 0.33 meters, which means that gives us F equal to 330 divided by 0.33, and that turns out that F is equal to 1000, and that's 1000 hertz. And that's the end of that question.